Hi, everyone. Thanks for joining us today. I am going to be your informal moderator. I'm Scott Smith, and I'd like to introduce our friend and colleague, Resa Rasouli, who is our expert in microfluidics and acoustofluidics. And he's going to talk about his work on micro lysing. So, Resa, all over to you.
Thank you, Scott, for the introduction. So let me move to my slides. Everything's good? Okay. Happy to be here. Welcome to the first session of Launch and Learn. Today I'm going to talk about low-intensity focused ultrasound as a strategy to lyse microclots. I'm going to start with a little bit of clinical background on why we are interested in these microclots in the first place. So microclots are associated with long COVID symptoms, and although COVID itself is no news, but the long COVID symptoms has been lingering for a while, and at least 65 million people in the world are affected by this. And you probably might know someone that complains that, well, after I got COVID, I get tired really fast, and I run out of breath. Or especially if they're doing some physical activity, they can feel some pain in their chest or etc. So also one of the main concerns and one of the main complaints is that there is some cognitive dysfunction, like brain fog, or having hard time to memorize things and names. These are not the only symptoms. You can see on the right that there are a whole spectrum of symptoms, not specific to one organ, multiple organs, and systematic. So it affects the whole body. So there's good evidence that shows that it might be related to the whole vascular system and dysfunction of the microcirculation. And the reason for that is that they saw these microclots as culprit, so they saw these microclots in the plasma of long COVID patients. So in healthy donors, these green dots that you see here, these are clots. So they're small, body can get rid of this. But then when you have long COVID, the rates of generation of these clots become faster, and they aggregate and become big enough to be able to clog microcapillaries and then disrupt the flow of red blood cells and delivering oxygen to organs. So this is one of the well-reported issues and might be the culprit for the long COVID patient. Probably not the only one, but one of the main ones. And microclots are not new. They are the hallmark of over 50 different diseases, from diabetes to stroke or inflammatory conditions, Alzheimer, etc. And one thing that makes them a bit hard to treat is that, especially with the long COVID microclots, amyloid fibrin microclots, is that their structure is a bit different than the regular microclots. So on left, you see a regular clot. The most abundant protein is fibrin and fibrinogens. They make this porous shape and structure that some enzymes like RTP can go sit on it and cleave it. The problem with long COVID amyloid fibrin microclots is that their structure is a bit different. So they're very dense. And also they have this protein called alpha-2 antiplasmin that blocks these enzymes to go sit and cleave them and degrade them. So biochemically, they are resistant. They're not responsive to the enzymatic lysis similar to the other clots. So one way to treat them is apheresis, which is essentially taking plasma out of your body and do the filtration similar to dialysis. But of course, it's very expensive. It is very invasive, and it's only prescribed for people or in a very acute condition. So since the biochemical and enzymatic lysis is not very effective for these microclots, so the idea is that using mechanical forces to lyse this, and probably the most known mechanical force for inside the body is ultrasound forces, because there are decades of research in sonothrombolysis that they showed that either as connection in the head of catheters or transcranial, they showed that, well, ultrasound is able to lyse clots and reopen clogged veins. Now, with ultrasound, we don't have just one effect. There are a spectrum of effects that you can use. One of them is boundary layer driven streaming. Essentially, whenever you have an oscillation, that oscillation creates counter-rotating streaming inside the fluid that can apply shear force on particles. The other phenomena is Eckhart streaming that happens when you have ultrasound propagates inside fluid, and it dissipates some of the energy and creates streaming and macro circulation. You also have ultrasound effects on the particles themselves, such as acoustic radiation forces that you can use to actually move particles from one place to another place. And then there is cavitation. You have stable cavitation where you have a bubble and you have low pressure and high pressure. In response to ultrasound, these bubbles contract and expand and create oscillation that is necessarily for this boundary layer driven streaming. But also you can, if you increase the pressure to a limit, you can actually make them collapse. And when the macro bubble collapses, then it creates some very strong macro jets. So alone, it can create different type of mechanical forces on fluid and particles, but also can be used in addition to enzymes for clot lysis by increasing the mixing efficiency, for instance. So that's the whole core hypothesis of this study, to use ultrasound energy and target it to clots, and as a non-invasive controllable clot disruption strategy. And then might have macro streaming effect, radiation forces, and macro bubbles that each one act differently to lyse these clots. So we want to study that and the possibility of lysis using ultrasound. Now, to do this, we have to first have a very good macroclot models, because we cannot each time go get blood from long COVID patients, right? So we have to make it inside our own lab. Second is that we want to have a very controlled and reproducible platform to expose these macroclots to ultrasound energy and make it as physiologically relevant as possible. Third is to have a quantification metric that look at this clot and see how they interact with ultrasound. And finally, understand how ultrasound can affect macroclots. If they're lysing them, then how they are lysing them. So the first step is to make the macroclots. There are a couple of ways that are reported using freeze-thaw cycles, or adding ALPS, or changing the pH. What we did was using a plated pore plasma and freeze-thaw cycles. So the green dots that you see here, these are macroclots that are marked by THD. THD is a biomarker for amyloid macroclots. When you have a macroclot, they bind to them and they become fluorescent, and then you can spot it. So it's also our verification method. So if you have fluorescent signal, it is amyloid macroclot. So we did dozen of cycles, and we saw that as we increase the cycle, we get more clots, and very good population of clots, enough for us to do all the tests. And then the size of the clots that we have around 20 to 25, which is also close to what's reported in the long COVID patient plasma. So that was the first step that made our life a bit easier, because we don't have to now go and get the plasma from the patient themselves. Now, the next step is to have a platform that is physiologically relevant and put these microclots and expose them to ultrasound system. Now, usually when you want to start a test in vitro, it's a petri dish and you put the clots and then you see whatever effect they have. But the problem with it in vitro is that it is very different than what actually microclots are experiencing inside your body. For instance, it's 2D, right? It's in the petri dish. And the way that acoustic wave propagates inside the fluid is very different. So what we made was these chips that are 6 millimeter, has a 6 millimeter diameter, and were similar to geometry of the actual popliteal veins. And then we used them to expose microclots to ultrasound system. Now, this is a bridge, this lab-on-a-chip method is a kind of bridge between the in vitro and simple petri dish studies and animal models, because, well, it is more relevant to your veins. For instance, the geometry is similar, but at the same time, it allows to do real-time imaging, something you cannot see in animals, right? So you can see the interaction of the ultrasound and bubbles and particles. So probably a video can show this better. So this is our chamber here. Now ultrasound is coming out of the plane, and these are 10 micron particles. And when we have ultrasound system activated, you can see a very strong streaming effect. Then you stop it, the flow stops, and then you can repeat it as many times as you want. So this allows us to look inside the chamber while the ultrasound beam is interacting with the bubbles and fluid itself. And then we can zoom in here, for instance, and then look at what different frequencies are doing. So for instance, this is the slow motion of the same frequency, and you can see the flow pattern. Whereas if you have, for instance, the same pressure, but with 1 megahertz, there's no movement. So overall, it allows us to, while doing the experiments themselves, see what's happening inside in a very controllable manner. So the geometry is very accurate, and it's micrometer level accurate, and you can see what's going on while doing the experiments. Now, the biggest step and the next step is to actually expose these microclots inside these chambers and see what ultrasound can do it. So these are our microclots, rather heterogeneous, distributed, and this is the zoomed in. And there are 20 to 30 micron, the bigger ones that are the problematic. And then when you expose them to ultrasound, this is what we see, very more homogeneous, fragmented particles that are size of 5 micron, 6 micron. And then 5 micron, 6 micron is the same size of your red blood cells, right? Red blood cells is about 7 micron. Now, it doesn't create any problem to go through your microcapillaries and solves the issue. So that was the big moment for us to see this really nice fragmentation of the clots from these larger aggregates to smaller pieces. Now, the next step for us was that, well, look at the other frequencies. So this happened at 150 kilohertz. And in the video before, you saw that, well, this streaming effect at 150 kilohertz is very strong. We did the quantification. We looked at two parameters: the average diameter of these macroclots. That was the first thing. And then the clots that are over 30 micron, because these are the ones that are problematic. These are the ones that can clog macrocapillaries. Now, what we saw was that 150 kilohertz, we see very good clot lysis, the image that I showed before, but it wasn't the case for other frequencies. And then we looked at the reason for that, and we experimentally verified that the reason was that we see some very small bubbles at 150 kilohertz, probably because the mechanical index at 150 kilohertz is higher. And we thought that, well, the reason for these stronger streams might be the bubbles. And the good thing is that, well, we can add macro bubbles to other frequencies and test it, because these macro bubbles are commercially available. These are FDA approved. You can use them for the same contrast agents that you use for ultrasound imaging, right? So we added macro bubbles at 300 kilohertz, and we saw, well, yes, we see the similar fragmentation at 300 kilohertz as well when we add macro bubbles. So the interaction of the ultrasound and macro bubbles and fluid is what creates these streams and the clot lysis. So you can see that it happens at 150 and 300, but also the average diameter drops for other frequencies as well. Now, for us, the next step was to see, this is purely mechanical effect at this point. I want to see the combination or have a comparison with the biochemical enzymatic clot lysis, which is the more standard way to lyse these clots, right? So first we tested lumbric-kinase, which is the fibrinolytic enzyme. It's derived from earthworms. And we looked at the clots after 1 hour of exposure to this enzyme without any ultrasound. And what we saw was that, well, compared to control, which is like no enzyme, and enzyme alone, we don't see much of a difference. And then when they expose them to ultrasound at different frequencies, the fragmentation happens, yes, but it's not that different from mechanical fragmentation alone, right? We kind of thought maybe if they make them smaller, then they completely dissolve with these enzymes, but didn't happen. We still see the small fragments, but it's mainly mechanically dominant. Now we tested stronger enzyme, which is nattokinase. It's from fermented soybeans. And then again, once we exposed it to the enzyme alone, without any ultrasound, it is similar to no enzyme. So enzyme and no enzyme, not much of a difference here. And then when we have ultrasound lysis, it does drop, but the pattern is still the same as without enzyme. So it's not doing much either. Finally, we tested RTPA. RTPA is the gold standard for thrombolysis for actual regular clots. And we exposed them to this enzyme alone, again, after 1 hour, not much of a difference. And then we had 150, 300, 500. It does fragment, but the pattern is similar to ultrasound alone. So it shows that, well, the idea that these are biochemically resistant is true because, well, we don't see any difference between enzyme and no-enzyme groups. And it might be that, well, yes, might be that, well, they shrink to the point mechanically, and then this RTPA dissolve it to the point that with our particle detection algorithm is not detecting properly. But what's important for us is that, well, we're sure that the mechanical effect is way, way more dominant than the enzyme. And that's what we want to explore a bit more, that how ultrasound is lysing these clots. So to do that, we want to study the interaction of ultrasound and fluid and the particles. And to do that, we are doing particle image velocimetry. So what we do is that in our system, we use high-speed imaging. So we get 240 frames per second. And then we have these tracer particles. And then we follow these particles' movement and displacement and see how frame by frame, how they're moving, and have cross correlation of these images. And then from the displacement of these particles, we can extract the velocity field and the flow field. So here you can see frame by frame. This is a slow motion, but this you can see the frame by frame how the field changes, and the field is not laminar, right? It's completely chaotic because it's not driven by the gradient of pressure. So we look at this, and then we extract a flow field for different frequencies. Now, this is the heat map of magnitude of velocity in meter per second. And you look at different frequencies and different duty cycles. And what we see here is that as we have lower frequencies, then the magnitude of velocity increases. And also as we increase the duty cycle, the magnitude of velocity increases. Kind of what we saw in the videos as well and in the cloud Lysis as well. Now, the magnitude of velocity and flow field is important for us, but what's more important is that we can deduce the force and shear rate from fluid that are applied on the clots. So shear rate is essentially how layers of fluid kind of move and then apply force on these clots that can either lyse them or elongate them. Now, this is the heat map of shear rates at different frequencies and duty cycles. Still, what we see is that lower frequencies, the shear rate is way higher. And then you see it in 300, but then as you go to higher frequency, then, well, it drops. Now, the important part is that what most people use with these macro bubbles is 1 megahertz and higher, because the natural frequency of these macro bubbles and contrast regions is 1.5 megahertz. So as you move to the natural frequency, you should see stronger shear rate. But what we see here is that 150 kilohertz is more dominant. Now, if I take this RAW and put it next to our clot lysis performance, you can clearly see that there is a good correlation between how high your shear rate is and how good your clot lysis happens. Now, it shows us that, well, first of all, shear rate is related to this, how good your, by predicting shear rate, you can actually predict how good your clot lysis happens. But at the same time, it also shows that the streaming effect is the dominance rather than acoustic radiation forces. Of course, there might be some combination of forces, because with ultrasound, you cannot always isolate one effect completely. But what's important for us is that, well, this streaming effect is strong enough to lyse the clots that we made from the plated pore plasma in the freeze-thaw cycle method. And then 150 kilohertz with bubble and without bubble was strong enough to lyse the clots. But then when we added the macro bubbles, then we could lyse at 300 kilohertz and to some extent on 500 kilohertz. The fibrinolytic agents were not very effective. also in line with what literature suggests. And the ultrasound effect, the mechanical effect, was way more dominant. And then our PIV analysis showed that, well, the velocity of magnitude is actually higher at the frequencies that are actually can lyse the clots better. And the mechanical flow and mechanical streaming effect is the primary reason for clot lysis. So we published these data and frontiers in bioengineering and biotechnology. The enzymatic study is in Journal of Thrombosis and Thrombolysis, and then the PIV is in the preprint. So you can read more detailed outcomes here if you're interested. And what we're doing right now is that since we got really good results with the static condition, now we are running to the flow condition and actually physiological relevant flow conditions, even very high flow rates like 14 ml per minute, which is similar to actually happens in your bigger veins. We have some good initial data that show that it is effective to create a streaming effect. What other thing that we want to look at is if we can actually do recanalization of the clot channels using ultrasound, and then after that optimize the parameters and make the minimum that is effective to do that. So with that, I want to thank you all for listening, and if you have any question, be more than happy to answer it.
Thanks for that, Reza.
Of course.
One question that is being asked is how easily does this translate now to preclinical studies, say in animals?
So one good thing was that the vein that we actually, the Lebanon chip system that we actually had was similar vein that is, you can find it more or less in animals as well and human beings. And what we are doing right now is to look at the flow rates that is similar that happening in the physiological conditions, and that's very important. So it is way more advanced than in vitro to the petri dish conditions. And just right before the animal study, we are omitting the necessity of doing animal study to actually look at it if it's actually having any effect or not. We are optimizing the parameters that once we go to the animal study, we know what exactly is happening and to what extent and what flow rate and how strong it can be. So it's just right before that we want to kind of, that's why Lebanon chip is being used, right? It's like an alternative to animal models in the sense that, of course, it's not as physiologically complex, but just right before that. Yeah, so something between the in vitro and the animal study.
That's great, thank you. One other question that came up is, do you think that this technique will eventually translate to treatments that are drug-free?
That was free?
Treatments that are drug-free.
Yeah, so far what we see is that the mechanical effect is way more dominant, especially for these amyloid that are resistant to enzymes. But also there is another opportunity that use it with the regular clots, but in combination with RTPA and the traditional fibrinolytics, because there are two effects at play right now. Is that one is that, well, the mechanical effect can disrupt them, but also you have the streaming effect that increase the mixing and also the binding of enzymes to this clot itself. So it can have synergistic effect as well. So it might be that this alone can work, but also with the regular clots, it can have synergistic effect with some drugs as well.
Yeah. Well, thanks so much for this. If there are any other questions, please drop them into the chat, or we're happy to follow up via email later. Thanks again, everyone.
Thank you.